Hello students, welcome back to another lecture in environmental modeling and simulation, and today we will continue our exploration of 2D nonlinear systems. So in the previous lecture we looked at Lotka Volterra model for competition, and we also discussed little bit about actually quite a bit about Lotka Volterra model for predation, and we noticed that how by changing just few signs, changing few terms, we get a very different relationship between the factors. Now I want to show you how by changing just some constants we end up with very different fixed points and behaviors around the fixed points. We are going to go back to our Lotka Volterra model of competition and then change some constants and see how that changes the behavior, what we see in the phase portraits. So if you remember, the Lotka Volterra model of competition between rabbit and sheep looked something like this. So if you remember our Lotka Volterra model of competition, it looked something like this, dr by dt. Okay. So in this case we had 4 fixed points, only one of them corresponded with coexistence, 2 with extinction of one of the species, and 1 was complete annihilation, which was unstable thankfully. Now let's change the terms a little bit, okay. What we are going to do is we are going to say that what if the model that we have looks slightly different. So let's say what we are going to do is we are going to change the constants a little bit, and let's say the model that we have looks slightly different. Now instead of the interaction between rabbit and sheep being at least twice as harmful for rabbits than for sheep, it is twice as harmful for sheep than it is for rabbit. So now our new model looks something like this. So not twice as harmful for rabbits, but quite harmful for the sheep now. So let's go ahead and find the fixed points. So the first obvious fixed point is R and S, both are 0. The second is R is not equal to 0, then what's the value of S? So if R is not equal to 0, then this term needs to be 0. So what we get is R plus S is equal to 3 from here. Now we can substitute this information here, and what we'll get is 2 minus R is equal to 0, which means R is equal to 2 and S is equal to 1. So when R is not equal to 0, the other possibility, now here what I assumed was that when R is not equal to 0, S is also not equal to 0. So this is when both R and S are not equal to 0. What if R is equal to 0 but S is not equal to 0? Is that a possibility? So R is equal to 0, right? R is 0 but S is not 0, then S needs to be S equal to 2. So what we get is 0, 2. So let's say now S is equal to 0 and R is not equal to 0. So S is equal to 0. What it means is that since S is equal to 0, 2 minus S minus 2 does not have to be 0. But here S is 0, R is not 0, right? So R is equal to 3. Okay, let's see if there is any other fixed point. And if you do the calculations, you will see that there are indeed some other fixed points, but they're negative. And for example, let's say when there might be other fixed points, but notice here that, this part needs to be redone. Okay, so we have 4 fixed points here. Now it is quite possible that we have a 2D nonlinear system that has more than 4 fixed points or less than 4 fixed points. All of that is dependent upon the kind of system we have. But what is important here is that, notice, by making the interaction between rabbit and sheep twice as harmful for sheep than rabbit, the coexistence point has changed. When they coexist, we'll have more rabbits than we'll have sheep. Now, let's see if changing these variables affected the stability of the fixed point. For that, we need to find the Jacobian. So let's go ahead and do it. I'm going to delete this because we are not using this equation. So we are going to differentiate this partially with R and then with S. Okay. Now let's find out the characteristic matrix for each of the fixed points. We'll start with 0, 0. Now in this scenario, our trace is positive and our determinant is also positive. Now trace tau square minus 4 delta so above the curve. So what quadrant are we dealing with? We're dealing with the first quadrant and we are not below the curve, we are above the curve. So we are here, we are in the case of unstable node, which is quite intuitive. 0, 0 is going to be an unstable node. Okay, now let's look at the next fixed point, J21, which is a fixed point where we are seeing a big change, right? So how does this fixed point change? This, if it does, the stability of this fixed point. So R is 2 and S is 1. Alrighty, so we are substituting the value of R and S here. Okay, and we get alrighty. In this case, tau is minus 6 and our delta is going to be 8. Our delta is going to be the minus 2 minus 4, that is 8 minus 2 into minus 2, which is plus 4, which is bigger than 0. So tau is negative and delta is positive. Now let's look at tau square minus 4 delta here. Perfect. Okay. Where do we lie? Tau is negative, delta is positive, we are outside the curve, stable node. System has changed. Instead of being a saddle, now the coexistence point is a stable node. So if the rabbits are not hurt as much as sheep are hurt more, the bigger animal is hurt more by their competition, then the coexistence might be a stable node. Right here you see the phase portrait has changed just by changing the coefficient. Now the relationship between the sheep and rabbit has not changed by changing the coefficient. It is still the relationship of competition. However, it's a different kind of competition that is favoring the rabbit and not the sheep. Now let's also take time to understand. So far, what we know is 0, 0 is an unstable node. The coexistence 2, 1 is a stable node. It's not a saddle point. Now let's look at 0, 2 and 3, 0, which is when one species goes extinct. So let's start with J02, Jacobian at 0, 2. R is 0, sheep is 2. Okay, trace is 1 and delta is 0. So when delta is equal to 0, if you remember, if you look at your graph, when delta is equal to 0, we are dealing with non-isolated fixed points. Now what happens at J 30? Here the rabbit are 3 and sheep are 0. Trace is -7. Delta is positive. Let's look at tau square -4 delta. 49 minus 48, it's above the curve. Great. So tau is -7, delta is 12. Tau is negative, so we are in this side, and delta is positive, we are in case of stable node. How fascinating. So what we are seeing is that there is a good chance that we'll either end up with coexistence, or we'll end up with a scenario where sheep die out because the interaction between rabbit and sheep is not conducive for the sheep, but it's very conducive for the rabbits. So the chances that, like just by looking at these 4 fixed points, the probability of coexistence is higher than it was in the previous case of competition. Also, the probability of sheep losing out to rabbit in this competition also seems to be higher. Of course, we have to draw the phase portrait to understand how the system works. But before we go there, I want to modify the model a little bit again and write down the model for cooperation. So because competition and predation are not the only relationships that we see in ecology, in environment, we also see a fascinating relationship of cooperation. In fact, human societies have grown around the whole phenomena of cooperating, agreeing on shared stories, shared myths, agreeing on certain facets that allow us to operate on such huge, immense level. So how do we model cooperation? Now, let's try to understand this. If 2 species, let's say, again, we are simplifying it too much. In an ecosystem, we have only 2 species and they are interacting with each other in a way that is mutually beneficial, then we can define that as a relationship based on cooperation. Now, we can assume 2 things. First, that the species cannot live without cooperation from each other. And we have some examples of this in environment where both interacting species require each other for survival. So in that case, how our model will look. So we are modeling cooperation, let me write that down. So in the first case, interaction is required for survival. So if the species don't interact, they're not going to survive. In the other case, interaction is not required for survival. But it is beneficial. Okay, so let's take the first case, you're calling case A, and second case is case B. So let's take the case A. In case A, where interaction is required for survival, let's say first species is dA, rate of change of first species, okay, let's not confuse A. Let's say the first species is X and the next species is Y, so dx by dt and dy by dt. They need to interact with each other to survive, which means that they will not have a growth factor which is independent of each other. If you look at other models, the growth factor, the net growth factor was independent of the other species. So the rabbits were very capable of replicating on their own without the other species. However, oh sorry, not here. However, remember when we talked about predation and predator-prey model, fox required to eat sheep to survive. So in case of fox, df by dt, fs, hunting the sheep or hunting the prey, was part of their growth model. Here it's not part of their growth model. Now here, since interaction is required for survival, interaction between x and y will show up in their growth model. So let's say it looks like this: axy, bxy. They only grow, they only replicate when they interact with each other. Cooperation is necessary for survival. Maybe one species is providing complex vitamins and minerals or complex organic molecules, and the other species is providing moisture or taking the bacteria or taking the species, the other organism towards nutrient-rich environment. So motility is required. Without each other, they can't survive. So notice this is their individual growth factor, but it depends on each other. They need to meet. Now, let's say this is sufficient, they rely on each other to grow and this is it. However, this will suggest that once they start growing, they're going to grow till infinity, because this is very much akin to exponential growth model. X is positive, y is positive, dx by dt and dy by dt will always be positive. So we know what's going to happen. The flow will always be towards plus infinity, which is not typically what we see in ecosystems. So we need something that talks about a limitation to the growth. And let's say the limitation to the growth is not coming from each other because they're helping each other grow, but then the limitation will come from the environment because environment has limited resources. So now we'll have a term that deals with limitation of resources, and it should remind you of logistic growth model. So here we have added a term for resource limitation minus Cx square, and remember that in logistic growth curve, the resource limitation comes from having the number, more number of the members of the same species. Now one thing to note is that for species X, which is the first species, interaction is required for survival. That is why the growth of this species, which is plus AXY, this term depends upon the second species Y. Only when X and Y interact, the species X can grow. This is not a condition for the growth of species Y. So you see, the condition for species Y says that interaction is not required for survival, but it is beneficial, which means the growth factor, the growth component of this model dy by dt would depend only on the population of Y. So we'll have B, Y here. So this resembles more closely the logistic growth model that we had. Of course, Y will also undergo resource limitation, so we are going to add a resource limitation term minus dy square. Now, the important part is that B is also benefiting from its interaction with A, even though the interaction is not necessary for the survival of Y. So now we need to add a term that shows that any interaction between X and Y is beneficial for the species Y. So here we add another term and multiply X and Y. Remember, when X and Y are multiplied, we are showing interaction or coexistence of both X and Y. So this is a model of a format of a model where we have modified Lotka Volterra models to simulate cooperation between two species X and Y. We can modify this model very slightly so to show competition. So in competition, the two species are competing with each other for the same resources. So they have their own independent growth rate and own independent resource limitation. So this is this should be very familiar to you. It should remind you of logistic growth curve. Now we need to introduce a term for both dx by dt where the interaction between the species is mutually harmful. So here interaction is again product and minus sign shows the harm. So now we have modified this model to show competition. Now coming back to cooperation, we can have a separate case. Let's call it case B. Case B is when interaction is not required for survival. So we need to modify this term. Interaction is not required for survival for either of the species, but it is mutually beneficial, in which case dx by dt will be equal to ax minus cx square dy by dt. This is just the growth part considering logistic situation. Now notice one thing, the growth of x does not depend upon y, the growth of y does not depend upon x because interaction is not required for survival or for growth, but it is mutually beneficial. So we need to add a term that shows that their interaction is helpful for both of them. So we have opposite of what we see in competition, plus exy and plus fxy. Now the third scenario that we are going to look at is that of parasitism. So case C is when one species is benefiting, X is benefiting from the interaction and Y is in loss. This is also called parasitism. Parasitism. Now in parasitism, the assumption is that X cannot grow without Y. So again, we can have two different scenarios here. One is parasitism, where X requires to feed on Y. So X needs Y for replication. So it's very similar to predation. Y is not happy, does not benefit from their interaction. Maybe there is no much loss too, so loss is not very much. So the equations will look like this: dx by dt, dy by dt. Now X needs Y for replication, so clearly the growth term will be like so. And then Y is not happy from the interaction, so we'll have Y growing on its own, some resource limitation, and then not very happy with this interaction. Now X species may also have some kind of resource limitation or some other predator. So there might be another negative term, a predation term or resource limitation or both. So let's take one last example for today's class. How will this writing change if X did not require Y for survival? Very simple change. X does not require Y, so this term changes. But X benefits from the interaction with Y. So let's make this AX. X does not require Y for replication, unlike mosquitoes. But every time it does interact with Y, it benefits. So we'll have a benefit term here. So it will look like so. This is a benefit of interaction. So this is an interaction where one species is benefiting from the other and the other one is suffering a loss. And there might be other things happening in a more complex ecosystem, like we might have a predation term, we might have another resource limitation term. There's also a possibility that Y does not really suffer from the interaction with X. It does not benefit, but it does not suffer. So let's take the example of vultures and eagles that roamed around our Indian cities and villages freely in 1990s. Their populations declined. We are again hoping that they will bounce back. What they were doing is that they were eating the dead animals and the dead tissues in our waste. So in a way, and back then, let's say our production of waste was not as much as it is now. Or maybe it was comparable, but it was not as much as it is now. So what they were benefiting from interacting with humans, because they were getting dead animals and food to eat. We were not directly benefiting from their presence. And now we know that they had very important ecological service to play. How will we modify this model to incorporate such kind of relationship where one species benefits but the other one is not at a loss? So very simple change. The other species is not at loss, so remove the loss. Now here X is benefiting from interaction with Y. We have this very nice benefit term here, but Y is not really at loss. Y is living their life. Y is only having resource limitation. Y may have other predators, depending upon how we're defining our ecosystem, may have other species that are impacting it, or just resource limitation. Now, if the assumption is X and Y are the only dominant species here, then we have to remove the predation term here and just keep the resource limitation term. So then our model becomes much simpler and it looks like this. There we are. This is an example where one species is benefiting, the other is not being bothered at all, neither benefiting nor being affected negatively. Students, I hope that today you got the tools that you need to modify this very simple format of writing models in a way that matches your system the best. Now, people have used this very simple language of writing models for modeling complex relationships between bacteria, as I said in previous lectures, modeling effect of GDP growth on greenhouse gas emissions and chemical kinetics. This is very diverse, and thank you very much. I hope to see you in the next lecture where we'll be talking about limit cycles, which is different from limit of growth, but we are talking about limit cycles. All right, see you in the next lecture. Thank you.